Yesterday we started interference topic number. What is interference? What is coherent sources? Is it audible? Is it audible, Anna? Yesterday we started interference concept number. What is interference? What is coherent sources? What is spatial coherent, temporal coherence? How to construct interference phenomena, superposition principle, and then Fresnel prism completed, conditions of interference completed. Then we go for determination of thickness of a transparent material using biprism. Biprism you completed yesterday. That biprism beta value, capital D value, 2D value we are calculated. Okay. Now that values we are substituting in the formula lambda is equal to beta into 2D by D. Then we are getting the wavelength value. Okay. That is Fresnel's biprism. Now we want to calculate and determine the thickness of transparent material. Thickness of transparent material using biprism. Okay, so here biprism, two slits compulsory is there. The distance between the slits is 2D. Then transparent material is A. Then the distance between one to other is X. Therefore, the biprism experiment can be used to determine the thickness of a thin sheet of transparent material such as glass, mica, etc. Here, transparent material we are using glass and mica. When a thin transparent sheet of thickness T and refractive index mu is introduced in the path of one of the interfering phenomena.
Ma'am, first tell about the topic names of topic names, ma'am, unit name.
Interference, ma'am. Applications of interference is there, no?
Okay.
In the biprism, Lloyd's mirror. So thickness of the biprism concept yesterday we completed, ma. Now we'll go for thickness of the transparent material or prism. I send you screen for that. So thickness of the transparent material, T value we are calculating using Fresnel's biprism experiment. So for that derivation part, everything is there on the screen now. Once you check it. So transparent sheet of thickness T and refractive index mu is introduced in the path of one of the interfering beams as shown in figure. Okay, the entire fringe system is displaced through a constant distance. The entire fringe system is displaced through a constant distance toward the path of the beam in which the plate is introduced. Between the plates, ma. Okay. So the T material you are introducing in between the two ma. So the entire fringe system is displaced through a constant distance toward the path of the beam in which the place is introduced. Now we consider the path S1P. Okay, now we consider the path S1P. It's clear the biprism experiment can be used to determine the thickness of the thin transparent material such as glass, mica, whatever it may be. You are using the thickness of the glass plate of glass or mica. When a thin film transparent sheet of thickness T and refractive index mu is introduced in the path of one of the interfering beams, as shown in figure. Now the entire fringe system is displaced through a constant. Now the fringe system is displaced through a constant distance toward the path of the beam in which the plate is introduced. Now we consider the path S1P. The length S1P minus T. Of this path travel in A with the velocity of light C. So total what it is, you are taking from here to here, then the thickness will be S1 to P, then minus T. S1P minus T we are taking, that is the path difference of first traveling wave. While the length of T is traveled in mica with velocity Cg. Therefore, the time taken by a wave to travel S1 to P, S1 to P is S1P minus T by C plus T by C. So, distance by velocity plus time by velocity. Move and front and back, forward direction and reverse direction, two values were adding with respect to T. T also there no thickness of the means that is also distance by velocity. Actual distance is S1P minus T by C. Both we are taken. Okay. Now S1P minus T by C is plus mu T by C. Here mu is equal to C by CG. CG is equal to C by mu. Now S1P minus T plus mu T by C. Total distance we have traveled, then it is S1P minus T plus mu T by C. Then in both the terms T is common, then we are taking S1P minus S1P plus mu minus 1 into T by C. That is the same, the time taken by a wave to travel from S1 to time taken by a wave to travel from S1 to P. For that, finally, what is the value you are getting here? S1P plus mu minus 1 into S1P plus mu minus 1 into T by C. Therefore, next what it is marked, the path difference. The path S1 to P is equivalent to an air path. Nothing but S1P plus mu minus 1 into S1P plus mu minus 1 into T. S1P plus mu minus 1 into T. Therefore, the path difference at point P is equal to S2P minus S1P. That path difference at point P can be taken as S2P minus S1P. First slit is S1, second slit is S2. The difference of the two is nothing but path difference. Therefore, mu minus 1 into T, which is equation number 1. Now the path difference at P is equal to phase difference is we are considering lambda by d. Here path difference is S2P minus S1P minus of minus 1 into T. S2P minus S1P value is 2x d by d. S2P minus S1P value is 2x d by d. Instead of that, you are substituting 2x d by d minus of mu minus 1 into T, which is considered as equation 1 in this derivation. Now, but we know that for nth maximum, the path difference at P, nth maximum, the path difference at P can be taken as n lambda. Nth difference at path can be taken as n lambda. Is it visible, ma'am?
Ma'am, you are saying from the old textbook, ma'am.
What, ma'am?
You are saying from the old textbook, ma'am.
Not audible, ma'am?
You are saying from the old textbook or new textbook, ma'am.
Yeah. That is heading is same, but it is not in your textbook, ma'am. Separate notes like that. Yes.
The college which they provided textbook here. In that we don't have this topic, ma'am. So you are asking.
Heading is there, my topic is there, but the derivation part is somewhat different that in textbook and here. So there just giving mixing and match my total derivation. Here I am giving just derivation part according to the topic.
Okay.
So same textbook means you can read in textbook also, no? So that how to derive the derivation I will show you. I will deriving the derivation part clearly step by step. Heading is there, topic is there in your textbooks also. Okay?
Okay, ma'am.
Now, I will share you a continuation of this one. So that here before what it is not 2x and d by 2x and d small d by capital D minus mu. The path difference P is equal to n lambda. Therefore, 2x and d by capital D minus of mu minus 1 into T is equal to n lambda. Therefore, for nth fringe 2x d by capital D is equal to 2x and d by capital D. Therefore, 2x and d by capital D is equal to n lambda plus mu minus 1 into T. Then xn is equal to what it is marked capital T by 2d into n lambda plus mu minus 1 into T, which is equation number 3. Therefore, in the absence of the plate, T is equal to 0. Therefore, the nth maxima is equal to, in the absence of the plate, T is equal to 0. Therefore, nth maxima dn lambda by 2D. If S is the displacement of nth maxima, by introducing the mica, then S is equal to capital D by 2D into n lambda plus mu minus 1 into T. Then minus of dn lambda. Everything is clear in the derivation, ma? 2x debate. So xn value you want to find out, ma, that xn value is equal to d by capital D into n lambda plus mu minus 1 into T. Observing. Then xn is equal to d by capital D by 2 into small d into n lambda plus mu minus 1 into T, which is equation number 3. In the absence of the plate, T is equal to 0. The nth maxima is equal to dn lambda by 2D. If S is the displacement of nth maxima, by introducing the mica, therefore S is equal to capital D by 2D into n lambda plus mu minus 1 into T minus dn lambda by 2D. Now dn lambda by 2D plus d by 2D into mu minus 1 into T minus dn lambda by 2D. Then S is equal to what it is, ma? D by 2D into mu minus 1 into T. Therefore, thickness of the mica or glass plate T is equal to, finally what you are getting, S into 2D by mu minus 1 into D. One by one, stepwise we are calculating here, ma. Then thickness of the glass plate or mica sheet T is equal to S into 2D by mu minus 1 into D. That is Fresnel's biprism, and the thickness of the sheet using Fresnel's biprism completed. Is there any doubt? Ask who is that raised hand? Okay, next one, Lloyd's mirror experiment. Lloyd's mirror construction and experiment is there here. Lloyd's mirror experiment, important. So how to construct Lloyd's mirror experiment? The experimental arrangement of Lloyd's mirror is shown in this particular figure. So here consists of
interference, ma'am.
Yes, ma'am.
Some applications of interference.
Yes.
Ma'am, but we don't have the topics, ma'am.
What topics we have?
In applications of interference, we have interference by the method of division of wavefront and amplitude, Newton's ring by reflected light.
This is our, so yesterday we have completed that Newton rings, interference by wavefront, interference by amplitude. Division of wavefront applications, these two are Fresnel's biprism and Lloyd's mirror. And then division of amplitude is Newton rings, Michelson interferometer. Next continuation of that is Michelson interferometer and Newton rings. Before that, we have these applications.
Okay, ma'am, they did not provide in our textbook.
So here division of, that's what only I sent it clearly, like notes. You can follow that. Division of wavefront is Fresnel's biprism mirror. Division of amplitude is Newton rings and Michelson interferometer. In that division of wavelength, Fresnel's biprism completed. Now we will start Lloyd's mirror. After completion of Lloyd's mirror, we will go for Newton rings.
Okay.
Okay, in this Fresnel's biprism, and in Fresnel's biprism only thickness of the glass plate is there, that also completed. Next we'll go for Lloyd's mirror. This is also example or application of division of amplitude by interference phenomena. Okay. For that, here how to construct the Lloyd's mirror is given. The experimental arrangement of Lloyd's mirror is shown in figure. It consists of a plane mirror Mn. In the figure, it's shown clearly Mn. That Mn is mirror. A narrow slit S1 is illuminated by monochromatic source of light. A narrow slit S1, here S1 is there on the screen. No, that is illuminated by monochromatic source and monochromatic source of light. Further from light slit S1 is allowed to incident on the mirror Mn on at grazing angle. The reflected beam appears to diverge. The reflected light appears to diverge from S2, which is virtual image of S1, which is the virtual image of S1. Thus S1 and S2 serves as two coherent sources. S1 and S2 serves as two coherent sources. Okay, two coherent sources means the waves which is emitted by the waves is reflected and superimpose each other. We get the interference pattern. Okay, thus S1, S2 serves as two coherent sources. The direct cone of light, P S1 Q, and reflected cone of light P S2 B superimposed over each other and produces interference, fringes in overlapping region PB, of this screen. Therefore, central fringe, zero order fringe. Central fringe is zero order fringe. In the case of biprism, the central fringe, zero order fringe is bright, but now here central image or central fringe, zero order fringe is dark, because here you are calculating after construction PS to be superimposed over each other and produces interferences in overlapping region PB of the screen. Okay, ma. So these two waves acts as the superimpose of the waves. These two waves are acting as the coherent sources and superimpose the region of PB on the screen. Here we can find out the bright and dark. First central fringe is zero order fringe, nothing but dark. Therefore, in the case of biprism, next continuation of how to get zero order fringe at central, we can explain here. Now, what it is in the case of biprism, the central fringe, zero order fringe, the central fringe, zero order fringe is bright, but now here the central fringe is zero order fringe is nothing but dark. Generally, central fringe is commonly bright here, but in Lloyd's mirror experiment, we are getting the dark fringe because the reflected light has suffered. A phase change of phi. So as a result, the condition phase change of phi. As a result, the condition 2n pi for maxima. The condition for 2n pi for maxima in biprism is converted into condition for minima in Lloyd's mirror. Thus, central fringe is dark in Lloyd's mirror. Now, determination of wavelength. So how to determine the wavelength in Lloyd's mirror means Lloyd's mirror is mounted vertically up at a right of optical bench and placed along the length of the bench of the order. So that it is in Lloyd's mirror, what it is, another vertical slit is mounted, which is illuminated by a monochromatic source of light. No. After that continuation, what it is, ma'am? Wavelength illuminated by the monochromatic source of light, we can calculate here. Now the mirror is rotated. Now the mirror is rotated about an axis parallel to the length of bench. Now the mirror is rotated about the axis parallel to the length of the bench until distinct fringes are observed. Distinct fringes are observed in a micrometer eyepiece. Okay. So here, what is the value? If you know the beta value, same as in Fresnel's biprism, 2D value, beta value, and then capital D value, distance between slits and screen, and the distance between the two slits is 2D. Fringe width is beta. Then we can calculate the wavelength. That wavelength formula is lambda is equal to beta into 2D by capital D. Beta into 2D by capital D, which is the wavelength value in Lloyd's mirror experiment. Wavelength value in Lloyd's mirror experiment. Okay, ma'am. So nothing but these are Fresnel's biprism and Lloyd's mirror. Both are the division of wavefront or applications of interference phenomena due to wavefront, ma'am. Next, already we know that biprism and Lloyd's mirror. Then you can distinguish between these Fresnel's biprism and Lloyd's mirror fringes, ma'am. Okay. Now, what is the difference between biprism fringes and Lloyd's mirror fringes? We can calculate here. What means distinguishes of identify first. First one, what it is? The central fringe is white or bright in biprism. In Lloyd's mirror, what we are calculating? Zero order. Zero order means that is dark. The central fringe is dark in Lloyd's mirror. The central fringe is white or bright in biprism. The complete pattern of interference, fringes is obtained. The complete pattern of interference fringes is obtained in biprism. Ordinarily, a few fringes itself being invisible. Ordinarily, a few fringes itself being invisible in Lloyd's mirror. Next, third one in this Fresnel's biprism. What is Fresnel's biprism? The condition for maximum intensity. The condition for maximum intensity is given by phi is equal to plus or minus 2n pi. Phi is equal to plus or minus 2n pi, and n is equal to 0, 1, 2, 3. When n is equal to 0 means what happened, ma? 0 into pi, 0. When n is equal to 1 means 2 pi. When n is equal to 2 means 2 pi. 2 into 2, 4 pi. When n is equal to 3 means 3 to the 6 pi. Like that, we can calculate the minimum intensity, maximum intensity in a path difference of phi is equal to plus or minus 2n pi, where n is equal to 0, 1, 2, 3, so on we are taken. Now the condition for maximum intensity is given by Lloyd's mirror is 2n plus or minus 1 into phi. 2n plus or minus 1 into phi. Here n is equal to 0, 1, 2, 3. Instead of n is equal to 0, you are substituting that. What you are getting, ma? Pi. If you are substituting n is equal to 1, what you are getting? 2 into 1. 2 into 1 means 2. 2 plus 1, 3. 3 into 5, 3 pi. If you are substituting n is equal to 2, then if you are getting 2 into 2, 4 plus 1. 4 plus 1 means 5, 4 minus 1 means 3. Like that, odd numbers we are getting in a Lloyd's mirror. Now, fourth point in a biprism. The condition for minimum intensity. The condition for minimum intensity is given by phi is equal to what it is, ma? 2n reverse అవుతుంది. అక్కడ ఏదైతే maximum తీసుకున్నామో ఇక్కడ minimum అవుతుంది. ఇక్కడ ఏదైతే minimum తీసుకున్నామో అక్కడ maximum అవుతుంది అన్నమాట. These 2 points are one another converse. Next, the condition for minimum intensity is given by phi is equal to 2n plus or minus 1 into pi. N is equal to 0, 1, 2, 3. Similarly, the condition for minimum intensity is given by phi is equal to plus or minus 2n pi. Phi is equal to plus or minus 2n pi. That is n is equal to 0, 1, 2, 3. Next point. Next, the fringe width is the same for all pairs of coherent sources. The fringe width is same for all types of sources, ma. Therefore, the fringe width is the same for all pairs of coherent sources. The fringe width is different for a difference of pairs of coherent sources. The fringe width is different for different pairs of coherent sources. Next, sixth point. With white light, biprism produces a number of limited colored fringes with central white fringe. With white light, biprism produces a number of limited colored fringes with a central white fringe. With white light, Lloyd's mirror produces a number of black and white fringes with central dark fringe. Converses we are considering here, ma. With white light, biprism produces a number of limited colored fringes with central white fringe. Similarly, with white light, Lloyd's mirror produces a number of black and white fringes with centrally dark fringe. Then opposite undedi Lloyd's mirror. Lloyd's opposite undedi Fresnel's biprism. Is it clear, Nana? So up to this, biprism, Lloyd's mirror distinguishes between biprism and Lloyd's mirror over. Now colors of thin films and non-reflecting films. After that, we have, as your syllabus, Newton's rings, bed-shaped is there, but we'll discuss later. Now we'll go for colors of thin films. After that, colors of thin films is also important for 5 marks. How to get colors in interference phenomena due to in white light. Colors of thin films, we are observing light partially closing eye, we are getting the colors. No, ma. So that make how to get that colors of thin films we are observing here. When white light is incident on thin film, the light will split up by reflection at the top and bottom of the film. The light was reflection by the top and bottom of the layer. The splitted rays are in a position of interference. The splitted light is a position of interference. Position of interference, and the interference of these rays is responsible for the interference of these rays are responsible for colors. Therefore, the bright or dark appearance of the reflected light depends upon mu, T, and R. The light and the reflected light it depends upon mu value, refractive index, T value, thickness, and refraction coefficient R. Okay, the splitted rays are in a position to interfere, and the interference of these rays is responsible for the colors. Interfering rays is responsible for colors. The bright or dark appearance of reflected light depends upon mu, T, and R. Now, the thin film T is a constant, and for stationary position and stationary observation, R is constant. For white light, mu varies with wavelength. At a particular position of I, the interfering rays of only certain wavelengths will have a path difference. Only certain waves have a path difference, satisfying the conditions of bright fringe. As a result, only such wavelengths, means colors will be present. Such wavelengths will be colors present at the point of observation. Therefore, the colors for which the condition of minima is satisfied or absent, in other words, Therefore, the same point of the thin film, if the same point of the film is observed, with eye in different positions or different points of the film are observed with eye in the same position. Therefore, different set of colors is different set of colors is observed. That is called colors of thin films. Under the heading, we are considering this topic. Now, this is for only short answer. Now, non-reflecting films. One of the practical application of interference phenomena is the making of non-reflecting films. Making of non-reflecting films is the application of interference. Therefore, the reflection from a lens or prism can be decreased. The reflection from a lens or prism can be decreased to a minimum by coating with magnesium chloride. By coating with magnesium chloride, which is nothing but MgF2. Here, we can take the two transparent materials. One is mu1, one is mu2. First surface of refractive index is mu1. Second surface of refractive index is mu2. Therefore, first incident light ray is incident on the incident surface mu(I). It is reflected into the same medium. Some part is transmitted to the other medium. So that here we can take one is mu(I), one reflected ray is mu(R), and transmitted is AT. Okay, ma, AI, AR, AT. Refractive index of the first surface is mu1 and second surface is mu2. Now, consider a ray of light traveling in a medium. Consider a ray of light traveling in a medium of refractive index mu1 is incident normally. Refractive index mu1 is incident normally on a medium of refractive index mu2 as shown in figure. The ray of light partially reflected. The ray of light partially reflected with amplitude AR and rest is transmitted with an amplitude. Rest is transmitted with an amplitude AT. If A be the amplitude of incident light, if A be the amplitude of incident light, and I be the intensity of incident light. If A be the amplitude of incident light and I be the intensity of incident light, then I is directly proportional to A square. Then I is directly proportional to A square. That is equation number 1. Okay, ma? I be the intensity of light, then I is directly proportional to A square. According to Fresnel's equations, reflection coefficient R is given by R is equal to IR by I. Now, reflecting films continuation, I will share the page. Here you can find out the reflection coefficient according to Fresnel's biprism. According to Fresnel's biprism experiment, R is equal to IR by I. That equal to mu2 minus mu1 by mu2 plus mu1 into whole square. Generally, intensity is directly proportional to the square of the amplitude. Therefore, mu2 minus mu1 by mu1 plus mu2 whole square. For 8 glass surface, mu1 is equal to 1, mu2 is equal to 1.5. Then from equation 2, R is equal to 1.5 minus 1 by 1.5 plus 1 whole square. Then 1.5 minus 1 means 0.5 by 2.5. So 0.5 by 2.5 means 1 by 5 whole square. Then it is 1 by 25 means 0.04. Then percentage is 4%. Okay. Then T is equal to, in this way, when the light enters the optical instrument of air glass, in this way, the light is incident or enters the optical instrument at air glass surface. The light is lost by reflection, and this reflection loss is undesirable. And this reflection loss is undesirable. In order to reduce this value, what it is, the reflected light from the surface is transparent. The reflected light from the surface is transparent. Okay. Then what we are getting, I is for 8 glass surface mu that we are taken, and finally we are getting the glass plate. Light is lost by reflection and the reflection is takes loss is undesirable. In order to reduce the reflection loss from the surface, a transparent film of suitable thickness, is deposited on the surface. This film is known as non-reflecting film. In general, the non-reflecting coating transparent film produces destructive interference. Therefore, the thickness of the coating material is set. So that T is equal to lambda glass by 4. Nothing but lambda by 4 mu. Therefore, the refractive index of the non-reflecting coating lies between those of the lens and the air. Therefore, here what it is, mu I less than mu coating less than mu glass. That refractive index value gradually decreasing from one another. Glass is more than that of coating. Coating is more than that of light or air. Okay. Next, our topic is Newton's rings. Newton's rings and determination of Newton's rings, diameter of the dark ring, diameter of the bright ring, and wavelength of the light of Newton ring we are calculating. Now we will give the topics. Newton's rings. Next, our topic is Newton's rings. How to form the Newton's rings? Newton's rings, reflected light. So what is reflected light? Reflection, refraction, interference, diffraction, polarization. All these are the examples for light. Properties of light. Here in reflected light, how to form the Newton's rings that we want to be calculated. For that, when a glass plate is introduced or placed on the surface of the plain glass plate P. Figures are important here, A, B, C, D. 4 figures are there. Then first, how to form the Newton's rings are important. Then how central one is dark and then the intensity is less. Then intensity is more like that. Alternatively, bright and dark bands are formed. That was shown in figure D. Okay. When a plano convex lens with its convex surface, lens with its convex surface is placed on a glass plate, an air film of gradually increasing thickness is formed. Air film of gradually increasing thickness is formed between convex lens and plain glass plate. Here, because another wedge shaped film, how to find out here? Plain glass plate is there now. Plain glass plate P, and on the convex surface of the lens is touching that. Here gradually what happened from the center to edges, air film will be increasing order. Are you observing? Figure A. Here is there no gradually increasing surface we are taken here. This surface. Next. Now, when a plane convex lens with its convex surface is placed on a plane glass plate, an air film of gradually increasing thickness is formed between convex lens and plane glass plate. Convex lens placed glass plate, increasing convex shape is producing the. Okay. Then the thickness of the film at the point of contact, is 0. Therefore, if the monochromatic light is allowed to fall normally, and the point of intersection will be decreasing. If the monochromatic light is allowed to fall normally and the film is viewed in reflected light, alternate dark and bright fringes concentric around the point of contact between the lens and the glass plate are observed are known as Newton's rings. Now, experimental arrangement here. Okay, at the point of contact here. So, this first figure is a normal experimental figure, and second figure is how to get the incident ray AB is incident on the beam, and it is incident to the second surface C. Here, first surface it is reflected to T1, and second one it is reflected to second ray. These two are superimposed each other. You can observe clearly in the figure B. Here, the incident light ray is AB, that is touching on the first plane surface is B. It is incident to the second surface at the point of C. Here, some part is reflected, some part is transmitted. Transmitted ray touches at D. This reflected ray is 1. Okay. Then at that point of D, another ray, some part is transmitted, some part is reflected. Again, reflected ray is 2 at point D. These two are superimposed each other, then the concentric rings are formed that was observed in figure C. Here, thickness of the wedge-shaped film for plain glass plate and lens is T. Okay, ma. Here, center of the ring is C, radius of the ring is capital R, and distance between N to C is R minus T. From here to here T, then the remaining distance is R minus T. Okay, ma. All four figures are necessary to identify the interference in Newton rings. Due to the interference, how the Newton rings are formed. At the point of contact, intensity will be 0. Then we are getting at the dark band at the center. Then bright, dark, then bright. Like that, continuous concentric circles are formed. That continuous concentric circles are known as Newton rings. Okay, na? Once you read it, important question, ma. Wavelength, diameter, and difference between the diameters, bright and dark, and wavelength you want to be calculate now. First, understand the figures and how to form the Newton rings.
That is good.
Is there clear? Is there any doubt for Newton rings? How the Newton rings are formed? How Newton rings are formed? Is there any doubt? Then from that we want to find out the diameters and wavelength mark. The Newton rings experimental arrangement is shown in figure. Now, want to explain the construction of Newton rings figures, ma? The Newton rings experimental arrangement is shown in figure. Ma. It consists of mainly three parts, namely sodium vapor lamp with glass plate. First figure. First we are explaining first figure, ma. Sodium vapor lamp with glass plate and microscope, and then what it is in the combination of plano convex lens L and plate P.
బట్టలు మార్చుకొచ్చుకురా క్లాస్ ఏంది అర్థమవుతలేదు ఇల్లు ఏమో అదే చదువుకుంటూ పోతుంది ఎట్లుందో అట్లనే చదువుకుంటూ పోతుంది గిట్ట కూడా మార్చలేదు వాళ్ళంటే ఒక అమ్మాయి అంటున్నది మేడం ఎట్లుందో అట్లా చదువుకోబోతులేదు మేడం
Manidīpa.
అట్లా
Okay. First, here three combinations are compulsory. One is glass plate raising an angle 45 degrees with traveling microscope M, and the combination of plano convex lens and plain glass plate P. And it consists of mainly three parts, namely sodium vapor lamp with glass plate G at an angle of 45 degrees with a vertical traveling microscope M, and the combination of plano convex lens L and plain glass plate P. Now, a parallel beam of monochromatic light from an extended source is made instant on a inclined glass plate G. G which reflects it in vertical downward direction. Each ray of light suffers reflections from upper and lower surfaces of the thin air film formed between plano convex lens. Okay, plano convex lens L and plain glass plate P. Inclined glass plate G, which reflects it in vertically downward direction. Each ray of light suffers reflections from upper and lower surfaces of thinner film formed between plano convex lens and the plain glass plate. These reflected rays of light superimpose and produce an interference pattern. Consisting of alternate dark and bright fringes as shown in figure. As locus of all the points of air film, of same thickness, is this circle. So interference fringes due to all the rays appears to be circular ring. As the locus of that particular all points of same thickness is the circle. So interference fringes due to all the rays of instant light, at points corresponding to a particular thickness of air film, merge to appear as a circular ring. Okay, ma'am. Here, the central ring will be continuation of that part, ma. Here, the central ring is the dark and thickness of the rings. And the thickness of the rings goes on decreasing as we move away from central ring. Central ring is dark and the thickness of the rings goes on decreasing as move away from the central ring, because the thickness of air film goes on increasing as we move away from the point of contact of plano-convex lens. Point of contact of plano-convex lens. With the plain glass plate. Therefore, Newton rings are localized fringes. Newton rings are localized fringes. So, what is the theory involved in this? Now, we will go for theoretical part according to Newton rings. Here, AB is the monochromatic ray of light that was shown in figure 2. Okay, falls on the system as shown in figure 2. A path is reflected at C, which is goes out in the form of ray 1. Without any phase change. Without any phase change, directly it goes out like one ray. The next part, the rest of the part is refracted along CD. At point D, it is again reflected and goes out in the form of ray 2. Already I said starting only that 1 and 2 is interference, superimpose each other, it gives interference phenomena with a phase change of 5. Second one, it is a phase change of 5. First one, there is no phase change. Therefore, these rays 1 and 2 produce interference pattern consisting of these two. 1 and 2 produces interference pattern consisting of alternate dark and bright fringes. Therefore, if T be the thickness of the air film, then the optical path difference. If T be the thickness of the optical air film, then the optical path difference between rays and 1 and 2 is given by delta is equal to 2 mu t cos r plus lambda by 2. For normal incidence and an air film, r is equal to 0 and mu is equal to 1. Therefore, delta is equal to 2t plus lambda by 2. Okay. Delta is equal to mu t into cos r plus lambda by 2. If r is equal to 0 for normal incident and an air film mu is equal to 1. Substitute that values in above equation. We are getting delta is equal to 2t plus lambda by 2, which is equation number 1. At the point of contact of plano-convex lens and plain glass plate, transmission value is 0. Then from equation 1, it becomes delta is equal to lambda by 2. Which is the condition for minimum intensity. Thus, the central spot is dark. So, whenever delta is equal to lambda by 2 means it is the central spot that becomes as dark. Okay. Now we will go for what is the path difference. According to path difference, when it is maximum, delta is equal to L lambda is maximum intensity. Delta is equal to 2L plus 1 into lambda by 2 is the minimum intensity. And delta is equal to lambda by 2 means dark intensity, dark band we are getting here. So that now from the triangle, third figure is found as C figure. Now we are considering C figure. Here what it is, let QOP be the lens placed on a glass plate. POP be the lens placed on a glass plate as shown in figure. Here the surface POP is the part of spherical surface, with center C. Let capital R be the radius of curvature. And small r be the radius of Newton's rings. Capital R be the radius of curvature and small r be the radius of Newton's ring, corresponding to the constant film thickness, T. Now from triangle CNP in the before third C figure, CP square, hypotenuse square is equal to side square plus side square. Here hypotenuse square place we have the R square and CN is equal to R minus T whole square plus NP means R square. Now expanding A minus B whole square form is R minus T whole square. Then R square is LHS, then RHS side is R minus 2 whole square in the form of A minus B whole square. It becomes R square plus T square minus 2AB plus R square. R square, capital R square, both sides cancel. Then you have small r square is equal to 2RT. This minus 2RT, take that side plus 2RT. minus t square ma. If t less than or thickness of the air film is less than that of the radius of the ring, then t square also can be neglected. Then what you are taken, t is equal to 2 r square is equal to 2 into rt. Then t is equal to what becomes ma, r square by 2r. T is equal to r square by 2r, which is equation number 2. Before 1 is 2t plus lambda by 2. Now substitute equation 2 in equation 1. What is equation 1 ma? Delta is equal to 2t plus lambda by 2. 2 into what is t ma? R square by 2r. 2r square by 2r plus lambda by 2. Last step. 2r square by 2r 2 capital R plus lambda by 2. 2 gets cancelled. Then you have delta is equal to, then you have the delta is equal to what ma? R square by r plus lambda by 2. Delta is equal to r square by r plus lambda by 2. Is it clear now? Then bright diameter of the bright ring, diameter of the dark ring, we want to find out. When we are getting a dark ring, bright ring, we completed here. Now we want to find out diameter of the dark ring, diameter of the bright ring. 1, 2, 3, 4, 5 like that rings is there, means odd numbers are dark rings, even numbers are bright rings. Then you want to find out diameter of the bright ring and diameter of the dark ring. Okay. Are you following, ma? So here thickness of the bright fringe today class will complete. Next class we will go for dark ring, and then the wavelength of the monochromatic source of light using Newton's rings we will derive. Okay. So here when is a maximum intensity for the bright ring, maximum intensity is delta is equal to N lambda. From equations 3 and 4, what is the path difference in equation 3? R square by r plus lambda by 2. Here n lambda. LHS are equal means RHS are equating. Then you have r square by r plus lambda by 2 is equal to n lambda. Then r square by r plus, take this plus lambda by 2 that side. Then it is minus lambda by 2. Then r square by r is equal to what it is ma? 2n minus 1 into lambda by 2. R square is equal to 2n minus 1 into LCM you are doing. This r take this side by 2. Then radius is equal to diameter by 2. Diameter is equal to double of radius, no? Then dB by 2 whole square is equal to 2n minus 1 lambda r by 2. Here dn square, dB square by 4 is equal to 2n minus 1 into lambda r by 2. Okay, then dB square by 2, squaring both a by b whole square means a square by b square. dB whole square by 4 is equal to 2n minus 1 into lambda r by that 4 take this side ma. In this 4 is about cutting off 2 times. Then dB square is equal to 2 into 2n minus 1 into lambda r. Then diameter of the bright ring dB is equal to under root of 2 into 2n minus 1 into lambda r. Therefore, dB is equal to under root of 2n minus 1, which is equation number 5. Here the diameters of the bright rings are proportional to the square root of the odd natural numbers. Square root of the odd natural numbers. Next class we will continue. Okay. Dark ring and wavelength. Next class we will discuss. Is there any doubt today class? Is there any doubt? Shall I close the class?